Okay, let's look at a proof of this one. So we want to show that A cross B is equal to minus B cross A. So recalling the definition of A cross B, we have to identify the magnitude and the direction to know what A cross B means. Because whatever A cross B means, it's a vector, so we want to know its size and its direction. So this tells us about the size of this is the magnitude of A cross B. So this tells us what the magnitude of A cross B is. And you can see that if you do B cross A, you're just going to get the B here and the A here. So it's going to be the same thing. So we can say that the magnitudes are the same. That is, the magnitude of this is the same as the magnitude of this. So now we just have to show that the directions are the opposite direction. So they say, to determine the direction of A cross B, imagine curling the fingers of your right hand from A to B. So we can see from this picture that A cross B is going to be up, but if you do B cross A, then you're going to have to use, when you curl your fingers, your thumb will point down when you go from A to B, from B to A. So that shows you that A cross B points in the opposite direction of B cross A, and that's why we have the minus sign in front of it. Okay, some of the other properties, 2, 3, 4. So this is a kind of distributive property, so A cross B plus C can be written as A cross B plus A cross C. And this is another distributive. It's where you have the cross on the right-hand side. Still can do this. And this is what happens when you take a scalar and you multiply it times A cross B. You can put the scalar in front of the A, or you can put the scalar in front of the B. So here they just warn us that this is not true, or rather that A cross B is not equal to B cross A. So they say you have to be very careful about the order in which you write the cross product. And then they say that we don't have associativity, which is kind of surprising in a way. That is, if you do B cross C first and then do A cross that, it's not equal to A cross B and then cross C. They say even if you just take a simple example, like if A and B are both I and C is J, then if we do I cross J, I think we remember that we get K. So that's I cross K, which equals minus K cross I from up here. And we know that that is, from here, K cross I we know is J, so minus K cross I is going to be minus J. So here we get minus J, but I guess you can read through this, but in this case we get, in the other case we get 0. Let's see, why is that? Because I cross I, the angle between, if we do these two first, in other words, then the angle between I and I is 0. And remember, we have the sine of the angle in this for the cross product, where it was the cosine of the angle for the dot product. So the sine of 0 is 0, so this is just 0. So you get 0. You don't get minus j. So we don't have this associativity property. So that is something we have to remember. Okay, the next thing we want to do is, now that we have these properties of the cross product, can we get some kind of formula in terms of if A is written in terms of A1, A2, and A3, and B is B1, B2, B3, can we get some kind of formula for this without using, for example, the sine function? And what we're going to end up with is, if this is A and this is B, then A cross B is going to end up being here. So this formula here. Oh, sorry. sorry, this formula here. So this is what A cross B can be written as. So let's see, it says that there's an I component, of course, a J component, of course, and a K component, of course. And it turns out to be A2B3 minus A3B2. This is A3B1, A1B3, and this is a different one. So, okay, you might find this hard to remember, but let's see if we can see if there's any way to remember it. Okay, first of all, remember that I always has the A1 and the B1 elements, and J always has the A2 and the B2, and K always has the B3, and so the subscripts are for I are 1, J is 2, and K is 3. Now look at this. Here's I, and notice what's missing, which subscripts are missing. So 2 and 3 are there, but 1 is not there. So that's one thing we can remember, that the I in the result for A cross B won't have, as its coefficients for I, there won't be any subscripts 1. Okay, and similarly for J, there's no subscript of 2, and for K, there's no subscript of 3. Okay, so that's one thing we can remember. So that means, and then just remember that you're going to have two terms. We have two terms there, and it's going to be A2B3 and then A3B2. So those are really the only possibilities when you're leaving out the subscript of 1. And then the only thing is which one comes first. I don't see how to remember which one comes first. One of them comes first and one of them comes second. And here it's same thing, A3B1 and A1B3. Again, I don't see how to remember which one comes first. And then this one here. So except for knowing which one of these comes first in the difference here, we can sort of remember this. Okay, so anyway, let's prove this. So we're going to start out, like we said, that A looks like this, and B looks like this. So then A cross B is this thing, cross this thing. And now they're going to use the one of the distributive properties. Let's quickly look. So actually we have two distributive properties, number 2 here and number 3. Number 2 is when you have A to the left. I'm sorry, when you have cross to the left and then B plus C here. And number 3 is when you have cross to the right and A plus B here. So which one are they going to use? Probably either one will work, but which one are they going to use? They're going to use, from here they're going to pick out the B1 cross this whole thing. So that's actually the one that I think that was number 3 in the properties list. So anyway, it's B1 times this whole thing, and then B2J times this whole thing, and then B3K times this whole thing. So they have that. They have J and they have K. And then they're going to take this cross that, plus this cross that, plus this cross that. So you're going to get A1, B1, I cross I. And then A2, B1, J cross I. So you can see how they're doing that. Okay, now what can we do? We can use the property that, well actually it's not here, but we know that any vector cross itself has to be 0 because the angle is going to be 0, and so the sine of the angle is going to be 0. So any vector across itself is going to be 0. So this is going to be 0. And what else? This is going to be 0, JJ, and KK is somewhere, is going to be 0. So we can drop those. So they do that here. And so this is what we're left with. And then all they do is collect the i's. So you have an I term here and an I term here, and you just collect them and you get this. Okay, and the same thing with the j term. So we get this. We said that we can kind of remember this. So this is our formula for A cross B when A and B are given like this. So we can try this out. Suppose we have this cross this. So we see that we're going to take A2, which is 3. What was it? A2, B3. So you have to take cross Bijk. So that's this. So that's 3 times 2 minus A3, which is negative 2, times Ijk. This is times B2, but there is no B2 here because J is missing here. So the B component is 0, so times 0, and so on. So you just fill this out, and this is what you get at the end. Okay, so that's using this formula, or this result here. Okay, so now they admit that this is kind of complicated to do it this way, but they say fortunately there's a more elegant way to do this. So let's consider that next. So we're going to talk about matrices and determinants, and this is the first introduction in this chapter. So these are 3 examples of matrices. So this matrix we say has 2 rows. This matrix we say has 3 rows. And this has 4 rows. This has 3 columns. This has 2 columns. And this has 4 columns. So if the number of columns, 4, is equal to the number of rows, then we say it's a square matrix. And we call this, since this has 2 rows and 3 columns, we say that it's a 2 by 3. We always mention the the row first. So it's 2 rows by 3, so it's 2 by 3. 2 by 3, or 3 by 2, or 4 by 4. However, right now we're going to focus on what's called the determinant of a matrix, and we're going to consider only 2 by 2 and 3 by 3 matrices, because we're only doing this right now for the cross product. So we're going to define what we mean by the determinant, and we're going to consider matrices of size either 2 by 2 or 3 by 3. First of all, we're going to denote the determinant either this way or this way. Both of these will mean the determinant. Now this will get whatever we're doing here, it's going to end up with a number. So like the result is not going to be a matrix, it's not going to be a vector, it's going to be a number. Okay, let's see, how do we compute this number? So let's start with, suppose we have a 2 by 2 matrix. How do we get this number, which is going to be called the determinant of the matrix? So suppose this is our matrix. It's A, B, C, D. So this is a 2 by 2 matrix. The determinant is denoted with this symbol. It also can be written like this, the determinant of the matrix. And the calculation is just you take AD, so you take this diagonal, minus this diagonal, minus BC. So that's the calculation. Let's just look at an example. Let's see if they have an example. No, not a 2 by 2? No. Okay, so they don't have a 2 by 2 example, so let's go on to the 3 by 3 case. So the 3 by 3 case, so if you have a matrix like this, A, B, C, D, E, F, G, H, A, B, C, D, E, F, G, H, I, then the determinant, which is still the same symbol, same notation, and you still can do it like this, is equal to this mess here. That's a little bit hard to remember, but is there some way to remember it? I don't know. I don't want to think about that. But you can also do it like this. A times the determinant of this. So that the way to remember it is first you take A, the first A there, and then you block out this the column that A is in and the row that A is in. And what are you left with? This. So it's A times the determinant of this, and then you take the B and you block out the column and the row, and what are you left with? D, F, G, I, D, F, G, I. So it's B times that, but there's a minus here. And then next line is plus, and what's that? You take C, Block this out and block that out. What are you left with? D, E, G, H, D, E, G, H. Okay, and then now we have these, but these are 2 by 2, and we can use this rule for these. And that's the determinant for the 3 by 3 matrix. So here's another way they say that you can remember it. I'm not going to go through this, but you can read it. The way I just described it, I think, works fine, which is I said you block the row and the column. They have another way of getting the same result. You can look at it here. I'm not going to do it, but you do get the same thing here. And their way doesn't generalize beyond 3 by 3, but the way I described actually does if you do it the right way. Okay, so now we can see from our formula before for A cross B, let's just go back and see that. That was here. This is equal to this, but this is actually, what is this? This is actually A2, B3, A3, B2. Let's check, let me check that. You can see that A2, B3 minus A3, B2, you can get that by taking A2, B3, we can take minus B2, A3. So in other words, this term here is the same as this. So this determinant is the same as this. And this determinant is the same as this. And this determinant is the same as this. So we can say, instead of saying this, we can put the determinant there, and the determinant there. But you can simplify this what we just wrote. What is the determinant of this? So how would you get the determinant of this in the way that I described it? So first you take, you'd block out this, and you'd get I times this. That's what they have, I times this. And then you'd block out this one, so you'd get J times A1, B1, A3, B3, A1, B1, A3, B. So you'd get that and this. So we just saw that A cross B can be written this way, but we see that this can be written this way. So finally we can say that A cross B is this. So it's you form this matrix and get its determinant, and that's what A cross B will be. So how do we form it? We take the elements of A for the first row underneath the IJK, it's actually the second row, and then you take the elements of B, or the components of B, for the last row, B1, B2, B3, and then you form the matrix like that, and you calculate its determinant, which gives you this, and that gives you A cross B. So this is another way to remember, or this maybe is an easier way to remember what A cross B is. We still have the original formula for A cross B, which was here, but here, we had to talk about the magnitude separately and then the direction using the right-hand rule. But now we can take A cross B, and if we have the components for A and for B, we can form this thing, this matrix, and do the determinant of it, and that will give us the correct answer for A cross B. Again, what do? You do IJK at the top. The second row is the first vector in the cross product, so that's A1, A2, A3, and the third row is the second, or the last vector in the cross product. So if you want to try it out, you could do this cross this. So what do? You do IJK, then you do 3, 2, negative 1, 3, 2, negative 1, then you do 1, negative 1, 1, 1, negative 1, 1, and then you figure this out, and you get this, and that is the cross product. Okay, then we could do some examples. For example, if we want to calculate areas and volumes, we could actually use the cross product. So let's use vectors to calculate the area of the triangles whose vertices are A, 3, comma 1, B, 2, comma negative 1, and C, comma, C, 0, comma 2. So here is C, 0, comma 2, here is A, and here is B. And we're going to form these vectors, AC and B, AB. And they say that this area of this triangle is half of the area of this parallelogram, and the area of a parallelogram can be obtained from the cross product. Okay, I didn't remember this, but I guess the area of a parallelogram given with sides length A and B is equal to AB times the sine of the angle between them. So I guess that can be proved in geometry or trigonometry. I guess trigonometry. So therefore the area of this parallelogram is given by AC cross AB. So A or AB cross AC is the same thing in terms of magnitude. And so that is the parallelogram, and the half of that is the triangle. So that's one use of the cross product. So if we want to take an example, we had the example of these points here. So we need to figure out what AB is. So that's the displacement vector from A to C. So AB, first we have to recognize that these vectors are in the plane. So technically we can't use the cross product. But if we imagine that the plane is part of 3D and these vectors have no k component, we just assume that the k component is 0. So we can write AB. Remember, we'll take, going from A to B, we take 2 minus 3 and minus 1 minus 1. So that's negative 1 and negative 2. So that's what they have, negative 1 and negative 2 here. And the k component is 0. And then you can do the same thing for this one. Wait, did I do that right? Sorry, we just computed AB. And we can do the same thing for AC. And so AC, so this is AB, this is AC. We can do the cross product like this. We get negative 7k. So we have to take the magnitude of that and take half of it. So we get we get 7 halves as the area of the triangle. Okay, you can also do something for the volume of a parallel pipette, but I won't go through that. Okay, now they mentioned that in this example that I didn't go through, apparently this appears in the example. So A cross B dot C. Now, what kind of result is this? Is this going to be a vector or a number? So, well, this part here is going to be a vector. So we're going to have a vector dot another vector that's going to be a number. So this is known as the triple scalar product, A cross B dot C. They said that since A cross B dot C represents the volume of the parallel pipette determined by A, B, and C, which this is the problem up above that we didn't do, it follows immediately that A cross B dot C is equal to B cross C dot A. So these are all equal apparently. And they say you can convince yourself of that if you think about the right-hand rule. And they say that this you can also get the result of A cross B dot C using this. And they say we leave it to you to check the following beautiful and convenient formula for calculating the triple scalar product. Okay, so let's just try and remember this a little bit. So if you have this so-called triple scalar product, where you have one vector cross another, dot another. So what they're saying is that it turns out to be the determinant of this matrix. And what matrix is that? You take the first vector as the top row, the second vector on the second row, and C on the bottom. And apparently this will give you the correct result. Okay, this is an example from physics. We're not going to cover it. This is another example from physics. Okay, let's review what we've learned so far. So we'll talk about scalar multiplication, so that's k times a vector. We'll talk about the dot product. We'll talk about the cross product. Okay, so for scalar multiplication, first of all, we can say that when you multiply a vector times a scalar, you get a vector in the same direction as A. The magnitude is just the magnitude of A times the absolute value of K. If K is 0, you get 0. If A is 0, you get 0. It's commutative, it's associative, and it's distributive. Okay, dot product, result is a scalar. The magnitude is A, B, the length of A, the length of B, times the cosine of the angle between them. This is also called the norm of A and the norm of B. The magnitude is maximized if A and B are parallel, because in that case, when the angle between them is 0, the cosine is 1. That's the largest that the cosine can be. So it's maximized when A and B are parallel, and it's 0 if they're perpendicular. Or it's also 0 if either one is 0. It is commutative. Associativity is irrelevant since it doesn't make sense. Why doesn't it make sense? Because this gives you a number. You can't take a number dot a vector. It is distributive in this sense. And if A equals B, then A dot, I'm not sure what they mean by this, but A dot A equals this. Oh, I guess they mean if you're doing this, and if A is equal to B, then you have A dot A. And the cross product, the result is a vector, and that vector is perpendicular to both A and B. In other words, it's perpendicular to the plane that contains A and B. Its magnitude is, the cross product, the magnitude of the cross product is magnitude of A, magnitude of B, times the sine, not the cosine, of the angle between them. So it is maximized when the two vectors are perpendicular. This one was 0 in that case. And it's 0 if they're parallel, because the sine of 0 is 0. It's not commutative, it's anti-commutative, which means A cross B is equal to minus B cross A. It's not associative. This doesn't hold true. It's distributive in this sense. It's also distributive in this sense. And if A and B are perpendicular, then the magnitude of A cross B is just the magnitude of A times the magnitude of B. In other words, when they're perpendicular, this is just 1. And so you just get this part. Okay, some of the exercises are: find the determinant of this, find the determinant of this. Now this one is easy, it's just that times that minus that times that. This one you have to take 1 times the determinant of these elements, and then 3 times the determinant of these elements, and then 5 times the other determinant. And you have to do minus sign for the middle one, so minus this term there. Okay, if we want to do the cross product of this, we can try to remember that kind of nice formula they had, which basically said form a matrix with I, J, and K on the top row, and then these on the second row, and these on the third row, and then calculate that the determinant of that matrix. Same thing with this one, but you have to remember that the K component here is 0, and the K component here is also 0. Otherwise, this doesn't make sense, actually. The cross product you have to be vectors in R3. Okay, here's one, calculate the area of the parallelogram. We did an example of that. Or actually we did an example of the triangle, but you can do the parallelogram. So you have to find the displacement vectors first. Okay, how about number 13? If A cross B dot C is equal to 0, what can we say about the geometric relationship between A, B, and C? Well, this is a dot product of this vector and this vector. So in order for the dot product to be equal to 0, one of them has to be equal to 0, the 0 vector. So either C is the 0 vector, or A cross B is 0, in which case what? Here's A cross B has the sign in it. So in order for A cross B to be 0, either A or B is 0, hopefully that's one possibility, or the sign of the angle between them is 0, which means that they are perpendicular. No, sorry, which means that they are parallel. So what do we have? Either A and B have to be parallel, which then, then they're parallel, or C has to be 0. I guess that's what we can say. And here they ask us to verify this, what they call beautiful formula. So verify this beautiful formula. So I'll leave that to you.